All right, here's the review from Saturday morning notes. If you want to walk through them, that's great. If you just want to read through the notes, that's also good too. We mostly go through metals and a little bit of acetal chemistry at the end. The other review was mostly focused on NMR, IR kind of stuff. So if you're looking to review more of that, I'd recommend watching the Friday afternoon review. Other than that, let's get going with this.
So remember that when it comes to metals, we typically want to look for a reduction or an oxidation of the central of metal. I should zoom in a little bit so I can write bigger. And remember that whenever we're talking about redox or oxidation, redox is a gain in electrons, and oxidation is loss in electrons. So going through the 7 types of things, let me just pull up a picture really quick. Organometallic steps. Organo because, well, it's organic chemistry. So both beta hydride elimination, how should I write this? Beta hydride elimination and migratory insertion are simply opposites of each other. So beta hydride elimination goes in the forward direction and migratory insertion goes in the reverse direction. So say we just have a generic metal, so M stands for metal, or why don't I just write it out? Attached to, say, a carbon group. So because we're looking at the beta hydrogen, we're going to go alpha beta right there because it's the general nomenclature is alpha is like the first one away from the metal, and beta is the second one, gamma is the third, delta fourth, and so on and so forth. So we've got the metal. So as its name implies, we're gonna want to get rid of a H minus group, which is the hydride group. So what's going to happen is that the metal donate, or this bond between the carbon and the metal group, are going to donate its pair of electrons to the carbons right there. But this, once we eliminate this, what was that? Too many bonds? Oh, whoops. Oh, thank you. There we go. So once we donate that pair of electrons, this metal will have an empty orbital, which fortunately the hydride, or the bond between the hydrogen and the carbon, can simply swing over and attach, and thus we get double bond and the metal attached to a hydrogen. And so going the reverse direction is just migratory insertion, where we attach the 2 carbons back onto it. Yeah? Yeah, let's go over that. Migratory insertion.
Gesundheit.
So I'll take, say, this just to make it look a little bit different, plus the metal and hydrogen. So we've got to line up the metal with the hydrogen. The way I think it should happen is we've got the sigma bond between the metal and hydrogen going over here, so forming that as a transition state, and then the pi bond coming out and forming the sigma bond between the metal and carbon. So this is 1 and this is 2. But really, this is a concerted mechanism, so it's happening all at the same time. All right, does that make sense? Let's do purple. What? I just think I hear voices sometimes. Not actual voices, just every time I hear like the A sound, like when it's followed by two consonants or preceded by consonant followed by consonant, I'm like, is that my name? Okay. So now we're doing oxidation addition and going to reduction elimination. So as the name implies, these are in fact just opposites of each other. So how does oxidation addition work? So we've got the metal, we've got two bonds, or two atoms connected via a bond. The metal will simply just attach itself onto A, then the sigma bond from B will come and attach to the metal, so you will get A attached to B. And why is this considered oxidation? Well, typically A and B are going to be more electronegative than M. Most of the transition metals we've seen are electronegativity of like 1 to 1.2. So even with the most simple of organic compounds, even hydrogen or boron with like 1.8 and 2.1, they'll pull away electrons from the metal. I'll insert this note in here. Electronegativities are usually from about 1 to 1.2. Alright, and then, so the forward is the oxidation, and then the reverse is the reduction. Do you want to see the reverse for? Do you want to see how the reverse for the reduction works?
Yeah, sure. You said the electronegativity metal is one or the other one?
No, this is the metal itself. We've only provided you with like this corner on the left side of the periodic table for electronegativity values. But for transition metals, they're all basically the same. 1, 1.1, 2. Okay, so let's just work reductive elimination just for completion. So what we've got the metal attached to two different elements. All we have to do is pull this pair of electrons up from the B, pull the sigma bonds from the electron, or from metal to A, and we get A, B. And you see right here, it's gaining electrons. Hence, it's a reduction. And up here, when we attach it to a more electronegative element, we lose electrons. Hence, it's an oxidation. All right. Then the fifth one, which we have seen quite a bit of actually, is CO insertion. We've seen this mostly in the Monsanto process. This is simply we just take a metal, we have an R group, and let's draw out the full structure. Notice this carbon right here is severely electron deficient. making it a good electrophile. So this pair of electrons between the ligand and the metal will simply come over, attach to the carbon, and then one of the pi bonds will swing up onto the oxygen. So what you will get is M attached to C, O, and then your R group over there. So really this is not a, I would really call this more an R group transfer, because it's moving off the metal onto a completely different nucleus. And later on we're going to want to eliminate, because the acetyl group we generate here is a precious, precious chemical entity. I attended a seminar once that was like, in the beginning God made the heavens and the earth. He also created the carbonyl group. There is nothing quite like it in its splendor and majesty. What? What, the acetyl group? A whole bunch of reactions we've seen, like Grignard, addition, elimination. It basically gets us to the carbonyl compound we're looking for that we can use in lots of different reactions. Basically the aldehyde and ketone chemistry we see in its own. And with that note, there are two more. Do you want to go over the rest? So I've got transmetallation, and these two really have not gone over as much, so I would doubt that these are on the test. But transmetallation just means we simply move the metal groups around, move metals. And when it comes to ligand exchange, we switch locations on the same metal. So say we just have metal, we have R1 and R2 through a series of reactions. It becomes R2 and R1. That it doesn't, it's not just one step, it's going to require a lot of in-between steps, most likely through the CO insertion, reduction, elimination, hydride elimination, migratory insertion, etc., etc. As you see in this, so what's important to note about these first five is that it's basically something other than metal that we're trying to attach onto, whether we're trying to add it on or take it off. With this one, the transmetallation, we're actually working with the metals themselves. Well, in every reaction we're working with the metals, but here we're not just working with the ligands attached to the metal, we're moving the nucleus of the metals around. Make sense? And ligand exchange is just moving around what's attached. So really all these other things up here could be considered ligand exchanges, because replacing like A and B with a pair of electrons. Alright, gone over that a good amount. Alright, what would you like to do next? Yes, Brian? We did that right here. It is. It's where we convert the carbon monoxide into the carbonyl group. So we turned it into poison. It was poison ivy. Now it's lavender soap. All right. What would you like to go over next? Those were the 7 types of metal reactions. And the question will basically just be from your notes. So look at your notes again. Let's see. There is the Monsanto process, which is pretty important. You want to do that? Okay. So Monsanto, aka Food Hitler. I should probably erase that. Okay. So this goes through 7 total steps. And we need let's see. Besides the metal catalyst, we need methyl iodide, carbon monoxide, and I believe we need water. Water does not come in until the very end. And we make our cute and, again, precious acetyl group. So I guess they did do something worthwhile after all. So if we were to do this reaction by itself, just using these 2 ingredients right here, we'll take the carbon monoxide. Well, I'm trying to show you why we need the metal catalyst to make it work out the way we want it to. If we do this, we take the carbon and we attach it to we attach the backside of methyl group, cause the iodide to come off via an SN2 reaction. We would get OCCH3, but this triple bond, oops, don't erase it. See how that's going to get in the way? That's going to become an excellent electrophile for the iodide, which we just barely formed, which will come on there and cause the pi bonds to come off. So we get this instead of the group we want. And it looks like, so in place of this, whoops, I didn't want to erase it. So in place of, whoops. We want to get the OH group, but if we just throw in carbon monoxide and methyl iodide together, we instead get a methyl group, which is not quite what we want. So let's go through the process. So the key element in this reaction is the catalyst. However it's named, I don't know. It's probably like rhodium iodide carbon monoxide. For now, I'm not going to write out the full state of the carbon monoxide. I'll show it when we're actually using it. And just so you're aware, this has a total charge of -1. What? Probably. That's actually easier than you think it is. If we pretend we take off the iodide groups, they each take away a negative charge. So we say they take 1 electron away. Yes. And then the carbon monoxide has a neutral charge overall. So we say it takes away 0 electrons. So we're taking away 2 electrons. Let's see. We actually have 1 electron gain because of the charge right there.
Okay, so who tells you?
You need to know the charge to know what the oxidation state is. That's not the charge. That's not the oxidation state of but you have to use it in order to get to the oxidation state of the metal. So we start out, we gain 1 electron from the charge, we lose 2 from iodide, which means we have lost a net of 1 electron. If we lose 1 electron minus a -1, it becomes a +1 state. Or you can just do the math and remember, oh, it's just the opposite sign. Number of electrons. Hello. I don't have butterfingers. Alright. Now let's take this guy. Now I'm actually going through the full process. So the first element we want to add, and I'm going to leave off the -1 for now, but I'll label the charges as we go along. So here, I mean, not the charges, the oxidation states. So the first thing we notice is that with the iodide, the methyl iodide group, we're going to perform an SN2 reaction. SN2. We'll bump off the iodide, making rhodium, iodide, iodide. I'll put the methyl down here. Doesn't really matter which order unless you're thinking about the geometry or thinking about majorly reassessing your life. So the oxidation state in this case, so we still have the -1s, we still have the I minus, and then the carbon monoxide taken away, or not doing anything. The iodides are taken away too. With the methyl group, how many electrons is it taking away? It's 1. Why is that? It's because if we were to take the pair of electrons off, it would become methide. It would take it with a negative charge. So because we're taking we're taking away another electron, so we're going to have a state of +2. And I guess I probably should. Whoops. I should do it with Roman numerals because that's technically the correct way to do it. Unless you're doing with -1. Unless you're doing negative numbers, then it's negative Arabic 1. You can use either one, I don't care. It only so for every negative charge we experience. Because I'm leaving off the -1 charge. That's why you're confused. So we are taking away 3 electrons from rhodium, which would give it a +3 state overall, but there's still this -1 charge throughout. I'm just leaving it off so I don't have to draw the brackets every single time. Net charge of -1 in this compound. And now with the I minus that we generated in the first step, it is again just going to attach to the rhodium. Yes. Aye, aye, aye.
So is this only
They could. It doesn't have to be 2 steps. I'm just drawing it like that. Yeah, you could draw it like this. Whoa, that's where it's picking up the methyl and then that just comes right on, like so. Okay, what's the... Oh yeah, what are we trying to do next? So again, let's calculate the oxidation number. Now it's 3 because we've again added another iodide. We're taking away 4 electrons with the 3 IIIs, one with the methide, and then we've got the total charge of -1. So it's 3 minus 4 equals -1. Whenever you're doing metal reactions, it's a good idea anyway, just to keep track of your oxidation numbers. Okay, now here's where the magic happens. This is where we're going to do the migratory. No, it's not migratory insertion. It's CO addition insertion / the 1-2 shift. It's for a different class, pay no attention. Now, like I said earlier, carbon monoxide is an excellent electrophile. And what the methyl group, wait. Yeah, that's what happens. The methyl group will just simply come over and attach to that carbon, causing a pair of pi electrons from the carbon monoxide to go into the oxygen. So we get I, CO. There is our acetyl group. And so what's the oxidation number at this point? We took away -1. Wait, the oxidation number is still the same because in this case it would be a methide. Well, not a methide, but a carbanion. So the oxidation number right here is still Roman numeral 3. Even though they're dead, we still like them. Yeah, so it does not change the... Actually, I think it does because we got one... Let's see. We have 4 negatives attached. We still have a -1 charge overall. So it still has to be +3. We just shifted the negative. So the neutral carbon monoxide doesn't contribute anything to the oxidation state. We just simply shifted the negative over from the methide over to the carbon monoxide. So that's why the oxidation number doesn't change. Okay. So we've got that. Now this is where, again, the magic happens. Where we take an iodide group. What would I call it? Looking at our above reactions, I think we would call it a... This, I would say, right here is the ligand exchange. Because we're switching out the... Wait. Oh, no, that's not the direction I want to go. Or really, what do I want to do? It's coming from the pair of electrons in the carbon onto the iodide. Actually, I would do, this is reductive elimination. Because we're getting rid of 2 groups off of the group, and we're also gaining a pair of electrons back onto the rhodium. And so it has to go from, I'll draw it over here so it makes more sense. It has to go from the carbon to the iodide to form this guy. If it were to go the other way, we'd have this acetyl group right here. We'd have iodide. Basically, I'm showing you why it's not going from here to here, from the I to the C. Because if we were to do that, we would form this O minus group. But then the carbonyl would want to reform and simply kick off the iodide again. So if we added the iodide first, then it would basically do nothing overall. So we've taken the carbon, I should do it a different color. We took the carbon, pulled it over here, the iodide jumped back on, the pair of electrons from the iodide bond jumped back on, and woohoo, there's our acetyl iodide. Acyl iodide. And voila, we have regenerated our catalyst. And what's the oxidation number here? It's just 1. It went from 3 to 1. Oh yeah, I think I'm missing that. Really not so much. I think it just comes on there before we take the acetyl group and attach it here. It could be simultaneous. Check your notes for that again, but the CO addition
So this CO insertion happens first where we take the methyl and put on the carbon monoxide.
Draw the arrow from the carbon because it's the carbon, not the oxygen, attaching to the rhodium right here.
Then before we do this with the purple arrows, before we move the acetyl group to the iodide, you need to bring in the carbon monoxide. So that's something to do with like carbon monoxide on there that has like oxygen in its bond. Yeah, it does. Sorry about that.
before formation. Is that clear? I would think so, yeah. I don't want to redraw it because that would undo all my very neat work. You mean like right here? Yeah, you could put it right there if you wanted to. Now, do you want me to erase it and just redraw it? Okay, thank you. I don't want to redraw stuff. Okay, so we again have our catalyst and our acyl halide. Notice we're not quite there yet because we wanted to generate acetic acid, but because we now have this acyl halide group, it is possible to generate that. So let's just do that really quick. The easiest way I can think to do of it, you can do this with hydronium it's just way easier with base, because what you just bring on the electrons into the carbonyl, bring up the pi electrons. Oh, didn't zoom in. So then we get O minus, OH, I, and then we'll just reform the carbonyl, kicking off the iodide because it's the best leaving group. So overall we have acetic acid and HI. I mean I minus. Are you going to ask about HI?
Yeah, why does it make HI when like you had an H2O tag in it?
Right, so if we're going to, do you want to just do the H2O one really quick?
Yeah, because why doesn't like another H2O instead of
It really should. So if we take, so let's walk through it and then I'll answer your question. So we do that. Kick off the iodide, forming this. Then I. So you're asking why is it iodide versus water?
Yeah.
It really should be water. Oh. Well, yeah, that's because that's what we have. What? Yeah, and also that's what we have in the solution. So yeah, it really should be water, not the hydroiodic acid.
And would it take the proton once it's already kicked off the ion, or would it take it before the ion? Just to make it like a worse group? Is that what
You could do it either way, but iodide is still way better leaving group. You could take the proton before, or you could take it before you kick off the leaving group, or after you take the leaving group. It doesn't make a difference. Wow, we've accomplished quite a bit. All right. So there's your Monsanto. Let's look back at the list I provided really quick. 7 organometallic steps. Week 14. Is today just a metals day, basically? Number 12. Let's move on from metals. I would so number 10 is basically just listing off the different organometallic steps and showing examples of such. Number 11 is just the Monsanto process. Number 12, take a look at that. What do you guys want to do next? For this is my list of special suggestions. Oh, okay. Just check other emails I sent out. So aldol specifically is is reacting an aldehyde or a ketone. With an alcohol. Let's see. What do I want to do? Yeah, let's just walk through the reaction. So say we have a ketone and we want to add an ROH group onto it. The first thing, these reactions will require acid catalyst because remember that when we form the tetrahedral shape of the carbonyl carbon, we've got to have a good leaving group so we can reform the carbonyl and keep going forward. So acid catalyst, we'll just use, say, hydronium. Hydronium seems to be the only acid catalyst we've used. It isn't, but it is. So we'll pick up that proton, become OH plus. So that makes this, by adding the proton across, it makes the carbonyl more susceptible to nucleophilic attack. So we can just bring ROH in, attack that carbonyl right in the middle, cause the electrons to come up. And we have OHR plus. We have OH. And then the methyl group over there. This water, or this OH group over here, will simply pick up that hydrogen, dropping it back onto the oxygen. Is that clear? I need to redraw that. So we have the hydroxide, which just picks up this, or the alcohol group, which picks up the hydrogen, which then will drop its electrons back onto that oxygen. Wait, what am I doing? No, this is not where we want to go. Not unless we were trying to get rid of that alcohol group, which is not what we want to do. We'll just take, if we protonated it again, we'd produce the possibility of a leaving group, OH2 plus water. We don't want to do that in this case. We'll just take another molecule of water to deprotonate it, drop down the electrons. Ooh, that's not a good arrow. There's not a lot of space here. Oh wait, I can zoom in. There we go. And then we form OR, OH, and this is our hemiacetal. Work through this. Oh, so that's really the main reaction we've seen so far. There's also aldol condensation, which I don't really want to go over right now, but I'll just mention it. Aldol condensation. This involves the use of an intermediate called the enolate. Oh, your daily Buddha quote has arrived. This requires the enolate intermediate. And will require a base or an acid solution. And especially with this enolate intermediate, there's this term we call tautomerization. In biochemistry, it's actually a really big thing. Basically, the tautomerization is when we go back and forth between the alkene alcohol and the coordinating ketone species, or we will need the acid or the base to assist between moving back and forth between both of them. But know that when we do have acid or base present, this is actually quite a quick process. And I do think I picked out a couple of problems relating to that. So look at that before you go take the test.